Hello everyone, my name is Mohammed Ibrahim from Finra. I am one of the contributors to the Data Generator project, and I will be using this video to give an overview about the Data Generator project. Uh, so what is the Data Generator? Data Generator is a library that helps us in generating patterns based on a given model. Um, those patterns, of course, can help us either in testing or in developing another project, as we will see later on the uses of data generator. So based on that, we understand that data generator is not a random data generator. Um, Data generator also uh, can take the model that we provide to it and split the model into several smaller pieces. Those smaller pieces can execute in parallel, either locally in different threads, or they can be serialized and shipped to remote nodes and execute over a parallel execution framework like Hadoop. And so it can be used to generate big data amounts, and with our definition of big data is few terabytes, usually in less than a business day. And of course, the data that's generated should be satisfying the given model, so it has constraints. Um, so what are the areas that we found data generator useful in? We found that it's useful in performance and load testing, since the amount of information it can generate is usually big and large. We also found that it's useful in functional testing because the data that it generates follows and satisfies the constraints provided by the model. Also, the data that's being generated can represent user scenarios. So the data might be as simple as data that fills a table or multiple tables in a schema, but it can also be user scenarios. So the model can say that a user lands on a website or a web application, then the user fills the login user and password, and then the user clicks login. That's one scenario. Another possible scenario that can be generated is that the user goes to the web application, the user then signs up, and after he signs up, then they apply their credentials, user and password, and then they log in. So those types of scenarios can then be used to drive a UI automation testing tool, something like JTAF or Extended Web Driver, that will then control the browser and perform those actions. And so it can be used as well in UI automation tests. So, the fourth area that we found data generator useful in is generating data for a schema when we are developing an application and we don't have any data yet to develop against. And in some cases, when the application is in a very early stages, the developers might have a very good understanding of the data, what the data represents, but they might not have enough data to develop against. In such situation, data generator can be very helpful as well. Data generator is a library, so in order to make best use of data generator, we expect the user to have to write some Java code. The core library of data generator provides few functions. It provides us with the ability to load and parse a model. It provides us with the ability to split a model into smaller pieces, and provides us with the ability to distribute those pieces, whether locally or to change the manner of distribution and distribute those pieces remotely on a parallel execution framework. And it really doesn't doesn't require a specific framework like Hadoop, for example, but it provides some basic interfaces and functionalities that can help us accomplish this on whatever framework the user chooses to. And the last function after the internal pieces of the library generates patterns, it sends them to what we call a writer. And a writer is a piece of code that the developer writes, and it formats the output on the way he or she is expecting their application to read. So how does the model look like, and how do we represent the model to the data generator? For the purpose of the model, we use a language called SCXML. It's an XML-based file format. And SCXML is short for State Chart Extensible Markup Language, of course. SCXML has W3C standards, W3C drafts, sorry, just like HTML. There's various open source projects that use SCXML. There's an Apache Commons library that helps load and execute SCXML. There are various GUI editors for SCXML. We use SCXML to represent two pieces of the model. The first one is states, and the second one are transitions. That's how an SCXML file looks like. On the left side, we see a file and from the first look, it looks like a regular XML file. It has an SCXML tag in the header and another close tag at the very end, and in between them is the description in SCXML. So the first entity we find here is a state, and this state is called start. Data generator expects to find the state called start inside the model, and another one that's called end. And between start and end are the states that logically represents our model. So once the execution goes inside the start, the only thing that's present there is an unconditional transition that transitions the execution to another state that's called set v1. So if the execution goes inside set v1, it meets a tag that's called onEntry. And onEntry, the function that onEntry accomplishes is initialization. So once the execution goes inside set v1, whatever inside onEntry will execute. And inside onEntry, we can see there's 3 assignment tags. Now, SCXML, like any programming language, employs the concept of contexts. It can store the values of variables in a local context inside each state, and then there's a global context for the whole state machine. The Commons SCXML project uses several evaluators. One of the evaluators that it uses is the EL evaluator. EL is the expression language evaluator, which is used also by JSP. So those variables will essentially be stored in context inside an EL evaluator, because in data generator we choose to use EL. We can choose to use another evaluator if you want. So once the execution goes back inside onEntry, there are 3 assignment statements. The first one sets the variable var out v11 to one of the values of a1, b1, and c1. Set is a keyword that data generator defines, and it means that the value is one of the items inside the set. At any moment, it's only one of them, not the three together. So what happens in a state like that is essentially data generator will expand this state to the product of the three of those variables. And so the output of set v1, if we were to draw the state machine as a graph, will be 9 states beside each other. The first state sets v1 to a1 and v2 to a2 and the third variable to 77. And the second one will then be setting v1 to b1, then the second variable to a2 and the third variable to 77, and we'll keep looping on all of them. That's the effective graph that comes out of this state. So how does data generator execute the state machine? There are two phases for execution. The first phase, the data generator tries to expand the graph output of this state machine using breadth first search. So starting from the start node, the first node at the top, data generator will then open every child that comes under this start node. Then it will open every child under every child of those nodes, and it will continue doing that type of expansion until it reaches a certain given number that we give the data generator. And at that point, if it reaches that number, it will stop expanding the graph. And what will happen? It will store the state of every one of those nodes with the possible unexpanded children, and then we'll store it in a data structure that we call the frontier. So this operation of initial expansion happens in a part that we call an engine, and the engine needs to understand the model. So we provide an engine with the data generator that understands the SCXML and can do this preliminary expansion for an SCXML model. So once data generator reaches this point, it encodes and stores the unexpanded children inside the frontier. What happens then is that it serializes the frontiers and either sends them to local threads or remotely sends them to totally different compute nodes. It might be on Hadoop, for example. And when they reach at that site, all those frontiers will start executing. They will start expanding the graph of the state machine again, but this time they will do it in a depth first search manner. And the reason they will do it in a depth first search manner is because those graphs sometimes get very big. They can result into billions of rows, and if we continuously expand them in a breadth first search manner, we will sure run out of memory. So what they will do is that start from the last point that the engine reached, and they will continue going down through the graph until they will reach the end node. Once they reach the end node, all the variables will have been set, and they will send the output to what we referred to before as a writer. So the part of the system that decides how distribution is being accomplished is called a distributor. We provide a default distributor with a data generator that will distribute the frontiers to local threads. We also show in one of the examples, it's called the MR example inside our repository, how to perform distribution over Hadoop. But again, data generator itself does not impose or require a certain framework like Hadoop to be used. Someone else might have a good idea how to distribute or write a distributor that works well on GraphX or another one of the libraries of other systems. So the frontiers play two functions. The first one is after the engines reach do this preliminary breadth first search distribution, they get encoded and they are shipped to the remote nodes. And the second time the frontiers come into action is doing the depth first search, like we said before. Once the frontiers reach all the way to the end node, and before they send the data to the writers, they call what we call the transformers. Transformers can expand placeholders that the user put in the model, and the result of those expansion can be some formatted values that the user know about, or for example setting certain values to variables that comply with a certain or satisfy certain probability density functions, for example. So for example, let's say that we're modeling users in a supermarket, and the users are buying food, for example, and we know that in average the purchase is $15 with a standard distribution of 5, for example. In order to generate purchase or sale prices with that type of distribution, the user will have to put a placeholder for one of the variables and expand this placeholder in a transformer and write Java code that represents their probability density function that their model needs. So how do we put this together in a small Java example? The code that we see in front of us is from one of the examples inside our GitHub repository. We'll take a peek quickly when we'll go through it quickly now, and then we'll switch to IntelliJ and look at the code inside IntelliJ. So the first step, we need to open our model, and the way we open our model is by opening a resource and getting an input stream and setting that input stream to one of the engines that we created earlier. We don't see the creation of the engine here, but after we create the engine, we set the model to the engine. And then we tell the engine how much of breadth first search we want the engine to accomplish. We call it the bootstrapping phase. And here we told the engine just expand up to one node. If we expect to run, for example, 20 threads, then we should change this number to 20. And if we're expecting to run this over Hadoop and we have, for example, 200 nodes, then we should set the bootstrap mean to 200, because every one of them will result in one mapper at the very end. We then create what's called the consumer, and the consumer has two pieces of information. It has one or more transformer, and every transformer will look for a placeholder that the user puts and change it in a manner that the user needs, and one or more writers. And the reason we have more than one writer is that maybe we will be generating 100 columns, for example, and 10 of them is going to one table and 90 is going to another table. So, or we want to produce the data in multiple formats. We want to write the data both as CSV and XML, for example. The next step is to prepare the distributors. So as we said, we have the default distributor that we provide with the data generator distributes the computation over multiple threads. We create a distributor and we set the thread count to 1. If we need more than one thread, then we set the number here according to the number of threads that we need. We set the consumer to the distributor, and we initialize log4j, and then we call the engine. We call the process function from the engine, and we give it the distributor. What will happen after that is the distributor, the whole process will run and should produce the output to us. Now for the writer, I'll backtrack a piece here. For the writer, we provide also a default writer with data generator, and the default writer writes to an output stream and writes a set of columns or set of variables, and it separates them using pipes. So here we give it a string array. The string array contains the names of the variables that we expect the default writer to write to the output in that order. So that's of course IntelliJ, and the project that's open here is a clone of the data generator on the FINRA OS repository. The example here that we'll be looking at is DG example default, and the entry point is the command line class. That's the code that we just looked at from a moment on the presentation. It creates an engine, SCXML engine. Then, like we said, it opens the file, sets the input stream, sets the bootstrap minimum. It creates a consumer, adds the transformer and writer with the variables that we need to write to the output. It creates a distributor, sets the threads, and calls engine process. What we didn't see in the other in the presentation is picking at the transformer. So here's the transformer. What the transformer does is just loop over all the current set of variables. It has a function called transform, and the function that's called transform gets a class as a reference to what we call a data pipe. And a data pipe, it just has a map of all the variables and the values of those variables. So this map contains the variable name and the value of that variable. It loops over all of them and looks for a placeholder called custom placeholder and changes it to a random number. So it looks for that. If the value equals custom placeholder, then it generates a random number and sets the value to that random value. So where is this placeholder? If you look at the state machine that we have here, in the second state, set v2, we're setting the variable var out v3 to that custom placeholder. Also, one thing to notice about this state machine is that all the transitions are unconditional. We can optionally add conditions on those transitions, and those transitions, of course, will set the constraints for us. And that's what makes a difference in data generator. So let's go back to the command line class, and now we will execute this class and see the output. So and here it is. Now the default writer, as we said, just writes to a stream. And we remember here that we set the stream to system.out. That's the output stream. So it's writing to the console. And also our logger is writing to the console. So we'll see the output mixed up. The order of the output is the first variable, second variable, third, and then v2 and v3. And we remember from the state machine that the values that v1, which is in the first column, can have is a1, b1, c1. So it takes all those values a1, b1, c1. The second one can take values a2, b2, c2, which appear here in the second column. And the third one is always 77. And the fourth one, which is v2, takes only values 1, 2, 3. And the last one is the expression or the placeholder that we replaced with a random number. And like we said earlier, that can be, for example, a sales price with a certain given probability density function that the user implements. So that completes our preliminary introduction to data generator, and hopefully we get everybody uses it, and we get feedback from you guys. Thank you.